Up till now, what we have discussed is vector norms. Then we have discussed signal norms, and then we from the signal norms we saw the notion of LP spaces and LP extended spaces. Okay, now what we'll be seeing is something known as an operator. Now, where does this come from? Okay, so let's say that you have a system which gets an input u and gives you output y. Okay, so this system is basically an operator which operates on the input that is being applied to the system, and the output of the operator is essentially the output of the system. Okay, so we call G as the operator, and G is an operator that maps signals from a LP extended space to the same LP extended space. Okay, before we proceed further, in certain books or in certain materials, you might find additional subscript, no, not subscript, maybe a superscript, which essentially this n is basically trying to say that um, LPE is a collection of signals for whom the integrals will be evaluated from 0 to infinity and the functions map to Rn. Okay, so this n is essentially this. Okay, and as we had already discussed, this p is nothing but 0 to infinity not this raised to the power p dt, and you have a 1 by p. So the p here is used in the definition of the norm. Okay, so in certain textbook you would also find a superscript that basically denotes the Rn. Basically, from where would the function f to where would the function f map to. Okay, so the 0 to infinity domain gets mapped to Rn. That is what this n superscript would essentially mean. Okay, so yeah, in our discussions here, if I don't use the superscripts, for example, here when I say G is the operator that maps signals from LP extended space to LP extended space, then um, what I would essentially mean is they are essentially the same spaces. Okay, both the spaces are same, so the superscript is possibly the same. So I have dropped. If the superscripts are different, then I will explicitly mention them. Now, coming back to this, the system that we started off with, that the system is being represented by G, which takes in the input U and gives you output Y, and G is the operator that maps signals from LP space to the same LP space. Okay, so as I said, we'll call G as an operator. So G is an operator. The question that comes is And what are we really interested in before we go into operator norms is when G transforms the input U to the output Y, the magnification in U that is caused by G to get the output Y, will it remain bounded for all admissible inputs? Okay, or in other words, is G stable? Okay, so the questions that we are actually looking for is the magnitude of, or rather, sorry, not the magnitude, is the magnification caused by the operator to this input U to get Y is bounded or not. Okay, and this is to, this we are asking for all admissible inputs. Okay, or to put it in another way, is G stable? Is G a stable system? Okay, now here this G may be a linear operator or a non-linear operator, but as mentioned, it takes input from the LP extended space and gives you output in the LP extended space. Okay, so this essentially means that if U is in L1E, then Y will also be in L1E. Okay, this is just what we mean. If U is in L1E, then Y will also be in L1E. Now, what we are really asking is, and when I say we are going to look for magnetism, and I mean, okay, so what we are really asking is, though this thing holds, if U is in LP, if it implies that Y is also in LP. Okay, remember that if a signal is in the LP extended space, it necessarily does not mean that the signal also belongs to the LP space. Okay, so we know that the operator maps signals from the LP extended space to the LP extended space, but if we know that the operator maps signals from the LP space to the LP space, if this holds, okay, for all signals from LP space, if it all inputs from LP space, if the operator gives you a output which lies in the LP space, okay, if this is the case, then G is a stable system. This one we call G to be stable. Okay, it's not that if it maps inputs from the LP extended space and gives you output in the LP extended space. That is not when we call it to be um, stable. Okay, we call it to be stable when the G is actually mapping inputs from the LP space and gives you an output in the LP space. So this brings us to the notion of something known as LP stable or finite gain LP stable. Okay, so let's see what these are. The operator G is LP stable. I call it to be LP stable if there exists a class K function alpha, some class K function alpha defined on the interval 0 to infinity, and some beta that is greater than equal to 0. Please note that this beta is a finite non-negative constant. Okay, finite non-negative constant such that the L2 norm of the truncated y, okay, no, sorry, not L2, the LP norm of the truncated y is less than equal to alpha of the LP norm of the truncated u plus beta. Now, alpha is a class K function which essentially, so alpha belongs to alpha is a class K function. So what alpha is basically, alpha maps from 0 to infinity to R. Okay, and alpha is 0 at 0. Okay, or rather I should write it like this: alpha of x is 0 if and only if x is 0, alpha x is positive for all x not equal to 0, and alpha is monotonically increasing. So as the value of x increases from 0 towards infinity, the value of alpha of x also keeps on increasing. Okay, it's monotonically increasing function. So this is a class K function. Okay, now we say that the given system or the given operator is LP stable if I can find a class K function, and class K function defined on the interval 0 to infinity, because we are concerned over that interval, and a non-zero finite, non-negative finite positive finite constant, non-negative finite constant, such that this particular inequality is satisfied. Now, what is this inequality? It is saying that suppose there is a u from the LP extended space, and you are getting a y from the LP extended space. Now, for all u in the LP extended space, okay, the output that you get should be such that the LP norm of the truncated output, okay, should be less than equal to alpha of the LP norm of the truncated input plus beta. Okay, this should hold for all tau in 0 to infinity and all u in the LP extended space. This inequality should be true. Okay, we call this operator G as finite gain LP stable. Okay, now here the P that we are talking of is between 1 to infinity. Okay, so G is finite gain LP stable if there exists non-negative finite constants gamma and beta. So exist gamma, which is finite and non-negative, beta, which is finite and non-negative. I think I will write it explicitly here as well. 0 less than beta less than. So you have two non-negative finite constants such that for all tau in the interval 0 to infinity, so for all possible truncations, and for all u in the LP extended space, this inequality should hold. The LP norm of the truncated output must be less than equal to gamma times the LP norm of the truncated input plus beta. Okay. So if you notice the difference between the LP stable and finite gain LP stable, in LP stable we have a class K function indeed, but note that the right hand side of the inequality in LP stable cannot be expressed as a scaled version of, it's not just the scaled version of the LP norm of the truncated U, but in case of finite gain LP stable, what you see is in the right hand side of the inequality, it's a scaled version of the LP norm of U tau, or the scaled version of the LP norm of the truncated U. Okay, so for finite gain LP stable, you should be able to find the gain factor gamma and the bias factor beta. So beta is known as a bias. Okay, such that this inequality is uh, satisfied. That is why this is known as finite gain. So there is a finite non-negative constant that you can get so as to satisfy this inequality. Okay, now the L gain or the LP gain associated with this operator G is less than equal to this factor gamma. Okay, additionally, the gamma and beta that you would find for this finite gain LP stable system are not unique. Okay, so for a finite gain LP stable system, gamma and beta are not unique, as larger values will also satisfy the inequality. What I mean here is, if for a given gamma and beta, suppose the system is finite gain LP stable, if for given gamma and beta, suppose the relationship holds, then this would imply that the following relationship will also hold for all gamma 1 greater than gamma and beta 1 greater than beta. Right. So that is why these non-negative finite constants are not unique for a system. Okay. Now I named so from the inequality it looks like gamma is trying to tell you what is the amplification, what is the amplification that you can expect, and beta is trying to establish a bias. Okay, so beta is the bias, and this bias can be zero or non-zero, but it's essentially non-negative. Okay, now a non-zero beta indicates that the output is non-zero for zero inputs, right? Because let's say beta is non-zero. If you look at the inequality, and the system is already finite gain. So I should write this properly. For finite gain, or rather I should say for LP stable systems. Okay, and that is evident from the inequality itself. So if you look at the inequality, when the input is zero, the alpha of um, alpha of norm of u or gamma multiplied by the norm of u is also zero. So what you essentially have is uh, that the norm of y has to be less than equal to beta. Okay, so this indicates that the output of the system is non-zero. Okay, is possibly non-zero, because that is going to be less than equal to a non-negative number. Okay, so when beta is non-zero, then the output is possibly um, non-zero for the system when the input is zero. Okay, now what is the gain of the system? Okay, so how do you define the gain of the system? The gain of the system is basically the smallest possible value of gamma, okay, that you can use such that you will be able to find a beta corresponding to it to satisfy the inequality. Okay, so suppose the system is finite gain LP stable, then this inequality has to be satisfied. Okay, now the gain of the system is defined as this: the smallest possible value of gamma for which we can find a non-negative finite beta such that the above inequality required for finite gain LP stable holds. Okay, so the smallest possible value of gamma that you can find, for which you will also be able to find a corresponding beta so that the inequality is satisfied, then gamma is called the gain of the system. Okay, that is what is known as the gain of the system. Now, you once you find the gain of the system and a beta corresponding to this particular gain, so that the inequality is satisfied, then of course for finite gain LP stable systems only, then any other value of gamma and beta greater than the values that you have found will also satisfy the inequality. But this is the minimum that you actually require. Okay. So now, what you see here in the case of finite gain LP stable systems, if you see the inequality, this LP norms are essentially talking or giving you a sense of the energy contained in the signal up to a certain time. Okay, what time? It's a time tau. Tau represents the truncated version of the output. Okay, so what this is trying to tell you is starting from zero. hmm, Starting from zero, as you proceed, the energy that you see, or the energy that is contained in this output y, cannot be more than a certain factor of the energy contained in the output u and a constant beta. Okay, so the energy in the output y is due to the energy in the signal u and due to some factor that is corresponding to beta. Okay, so for finite gain LP stable systems, the energy in the output is due to the energy in the input, and what corresponds to this energy that is given by beta, it is the non-zero initial conditions. Okay, so zero initial condition essentially means the system is at rest. So for non-zero initial conditions, when the input is zero, you would see certain output. The system would evolve on its own, right? So the energy in the output is due to the energy in the input and the energy due to non-zero initial conditions. Okay, so this beta that you see here in finite gain LP stable inequality, it is essentially due to non-zero initial conditions. Okay, so the energy contained in the output is only because of the energy in the input and the energy due to the non-zero initial condition. The system does not have any source of energy on its own. Okay, now before so what I'm saying is the system does not have a source of energy of its own. Okay, had it had a source of energy of its own, then what would have happened? Under zero input, the output should also have a tendency to increase the energy as time progresses. Okay, so if it had a source of its own, then under zero output conditions, a finite gain LP stable system would have been such that the output would have a tendency to have an increase in its energy as time progresses. Okay, but that does not happen for finite gain LP stable systems. See, If u is identically 0, then this would indicate that this is also 0, which would essentially indicate that a finite gain LP stable system under a 0 input would essentially be satisfying this for some beta greater than equal to 0. And this beta is a finite constant, and this holds for all tau in the interval 0 to infinity. Correct? Which essentially implies that y under the output obtained under under the zero input is essentially going to be a LP signal. So the output under zero input for a finite gain LP stable system will always be a signal lying in the LP space whose L norm would exist. Okay. Why? Because this inequality is holding for all tau from 0 to infinity, and the right hand side of the inequality, which is beta, is independent of tau. So y has to be in LP space. Now if y is in LP space, then the energy contained in y cannot be infinite, it has to be finite. Okay, so that is why when there is no input, the energy, when there is no input, the energy contained in the output signal is always bounded. Okay, and that is why the system cannot have a source of energy on its own. Otherwise, the output would have a tendency such that it will see an increase in the energy. Output will have a tendency so that it sees an increase in its energy, right? Okay, we call the system G to be causal. What does causal mean? Causal essentially means that the output is because of an input. Okay, so if you are seeing a response, it is because something has happened. Okay, so it's a cause and effect relationship that you would have. Without a cause, you will not see an effect. So the system is said to be causal if the value of the output y of t defined as this at any time t depends only on the values of the input up to time t. So if you see at a time instant, whatever output you see is only because of the inputs up till time t. Okay, not because of inputs that are going to come. So this essentially means y tau is nothing but this u up till tau instant. Y at tau instant is nothing but not sorry, I used h z up till tau instant is because of the operator g acting on u up till the tau instant. Okay. Okay. Now, with all these discussions, we come to something known as a L2 induced norm for LTI system. Okay. Now, suppose you have a system which is of this form and G is a LTI system and is stable. Okay. Then if G is stable, then we know that if U belongs to L2, then Y also belongs to L2. Okay, we are talking of L2 induced now. Now, the L2 induced norm for this LTI operator G is defined as supremum of the L2 norm of Y by the L2 norm of U over all the inputs that are L2 barring the zero input. Okay, so you take the ratio of the L2 norm of the output to the L2 norm of the input for all the inputs that are in L2. Okay, except for the zero input. That is what that is what gives you the L2 induced norm. So this is essentially something of this form, which is norm of GUL2 divided by norm of this norm of GUL2 divided by norm of UL2. Okay, so what this is essentially trying to say is what is the maximum amplification that the system would impart to all admissible U's in the L2 space, as far as all admissible U's in the L2 space are concerned. So this L2 induced norm is essentially talking of the maximum amplification that the system G can impart to the input U. Okay, for all U in the L2 space, because we are using L2. Okay, and this can also be known as the gain of this L2 system. Okay, so we'll have more discussion on this as we proceed on this topic. So, to just recapitulate, what we had was we started with a system that maps signals from LP extended space to LP extended space, and we are interested in seeing whether the magnification caused by this particular system to the input U is bounded or not. And from there we established there are establish two definitions of stability for such systems. One is LP stable, and another is finite gain LP stable, with the difference between the two stability definitions being one uses a class K function and the finite gain LP stable uses a special class K function, which is just a linear amplification of the input U. Then we saw what is the LP gain that is associated with G, or what do we know, what is the value of gamma that we can call as the gain for the system. And then we saw that for LP stable systems, if beta is non-zero, then for a zero input, the output may not be zero, and beta being non-zero essentially indicates that the system has non-zero initial conditions. Then we saw the definition for the gain of a system, and we also deduced that this inequality that we have in hand is indicating that the energy contained in the output is due to the energy in the input, and the energy of due to the non-zero initial conditions that are there in the system, and that this system does not have a source of energy on its own. Whatever it gives you as an output is because of the input and the initial condition that are there in the system. Then we saw when can this system be called as causal. Please note that most of the system that we would deal with is are causal systems. And then we saw the definition of L2 induced norm for LTI systems, which is essentially trying to say that what is the maximum amplification that the system can impart to the input U when you get the output Y. Okay. In the next lecture, we'll see some examples where we try to establish whether the given system is LP stable or finite gain LP stable or not. Okay. Uh, so we'll stop here. Thank you.